Imagine we have a vector, let's call it A. This vector has both direction and length. Now, what happens if we multiply this vector by a number? For example, if we multiply this vector by a scalar number like 2, half, or even -4, well, we definitely get a new vector, but with some important changes. Let's look at the different cases. First, what if k more than 0, meaning we multiply the vector by a positive number? If we multiply a vector by a positive number, the new vector will point in the same direction as the original vector, but the length will change. If you multiply by 2, the new vector will be twice as long. If you multiply by half, the new vector will be half as long. So the new vector will stretch or shrink, but it will still point the same way. Look at the diagram. We have the blue vector as original vector with vector A. If you multiply 2 to it, we get the green vector. As you can see, it's twice as long, but point the same direction. And if you multiply by half to the blue vector, you get the orange vector, which is in the same direction but half as long. Next, if k is less than 0, meaning we multiply the vector A by a negative number, for example, negative half or -2, the new vector will point in the opposite direction. The length will also changes depending on the size of the number. For example, if you multiply by -2, then now we have a new vector which is twice as long as the original vector, but point in the opposite direction. This is what you can see from this green vector by -2a as compared to the original blue vector a. If you multiply negative half to the vector a, now you will get the yellow vector which is half as long as the original vector, but also pointing in the opposite direction. Now look at what happens when we multiply a vector by a scalar in component form. Suppose we have a vector, vector A is of this column vector, A1 over A2. Now we multiply this vector by a scalar k. We can write it as k multiplied by vector A equal to k multiplied by column vector A1 over A2 to give you a column vector of ka1 over ka2. This means that we multiply each component of the vector by the scalar k. For any vectors a and b and real numbers m and n, the following rules apply. The law of scalar associativity means that we can multiply scalar in any order when applied to a vector. Here you can see there are two scalar, m and n. If you want to multiply them, both of them to the vector a, you can choose to multiply in any order, meaning you can choose to multiply by m with the vector a first, or you can choose to multiply by n with the vector a first. It does not matter. Next is the scalar distributivity over vector. It means that we can add the vector first, then multiply by the vector. For example, if you have ma plus na where m and n are scalar, you can choose to add m and n first before you multiply by the vector. You will get the same result. Lastly, the last law of vector distributivity over scalar. This rule is about factoring out a common number called a scalar from two scales vectors. When you see ma plus mb, it means you take vector a, search it by m. You also take vector b, search it by m. Then you add the results together. But instead of doing that in two separate steps, this should let you do it in one step. First, you add the vectors a and b. Then you multiply the results by m. So the equation kind of say you can stretch first then add, or you can add first then stretch.